Hello everyone. Today I wanted to make a tutorial on the Lattice-Boltzmann method for fluid flow simulation in Python. And the way I wanted to do this was in a way in which is as simple and as accessible as possible for people that might not know incredibly high-level mathematics. I feel like a lot of the other tutorials out there in the internet are very, very complicated and very, very obfuscated. However, this write-up by Philip Mocz is incredibly effective, and with his permission, I'm going to be making a video walkthrough of it. That said, before you watch this video, you should very, very much read this article. It will explain all of the concepts that will go into the code, and then once you're done with that, then I will walk you through the code itself. Now, my code is going to be slightly modified because there are certain places in which Philip's code is redundant, and there are points in which it's also a little hard to understand. So I'm going to try and streamline that a little bit with my own version. However, fundamentally, it is the exact same thing. And this is going to end up with something that looks like this, a very, very cool simulation of fluid passing over a cylinder using the Lattice-Boltzmann G2Q9 scheme, which again, you can read on this article about, but essentially the code is going to be separated into two parts, the part that handles the streaming and the part that handles the colliding. So the streaming is what essentially is the sharing of velocities between neighbors. So how the Lattice-Boltzmann method fundamentally works is that it is going to split up our entire domain into these lattices. And each lattice is going to be able to contain 9 possible velocities, and you could see them here. It can either contain a stationary velocity, or it can have an upward velocity, or a downward velocity, or a velocity that's traveling up and to the right. And what happens is that when we stream these velocities, the velocity in this cell traveling upward goes to its neighbor directly upward. The velocity traveling directly to the right goes to its neighbor directly to the right. The velocity in the bottom left goes to its neighbor in the bottom left, and the same for every single cell. And that is how it's going to it's going to stream the velocities throughout the entire domain. And when I talk about this entire lattice, I'm going to refer to it either as a lattice or a cell. When I talk about each one of these potential points of velocity, I'm going to call it a node. And when I refer to the direction that each one of these nodes can travel in, which is a set value, I'm going to call it that node's discrete velocity. So for example, the discrete velocity of this node is 1, 0, 0, because it is traveling with 1 in the x direction and 0 in the y direction. That said, jumping straight into the code, the first thing we're going to go ahead and do is import our dependencies, and we're going to only need 2. We're going to import NumPy, and then we're going to import pyplot as well. And for our own sanity, we're going to abbreviate NumPy as NP and then jump straight into it. So the first thing we're going to do is we're going to go ahead and define our main function. We want this to be the only thing that runs. So we are going to do if name is equal to main, then we can make sure to just run this portion of the code. So the first thing we're going to do, other than that, is define our constants. And the first constant that we want is the amount of lattices in, or the amount of cells in our x direction, and that is going to be 400. We want 400 cells across our x dimension, and we want 100 across our y. Then we're going to define our tau, which is our kinematic viscosity or timescale. It functions as both. And then lastly, the amount of iterations in time we're going to go through, which I'm going to call a nice healthy 3000. So next, we're going to go through our lattice speeds and weights. So we're going to have 9 different velocities. Again, it's 9 different velocities, 0, 1, 2, 3, 4, 5, 6, 7, and 8, or 1, 2, 3, 4, 5, 6, 7, 8, 9, depending on whether you start counting at 0 or 1. And each one of these is going to be able to take on its distinct discrete velocity. So we're going to define these discrete velocities, and we're going to do that. I'm just going to write it out first and then explain it directly after. We're going to create a NumPy array that is going to have all of the x values of our discrete velocities in order. So 0, 1, 2, 3, 4, 5, 6, 7, 8. And it's going to go 0, 0, 1, 1, 1, 0, negative 1, negative 1, negative 1. We're going to go ahead and just copy this for the y discrete velocities, and that's going to look like 0, 1, 1, 0, negative 1, negative 1, negative 1, 0, and 1. And I'm just going to go ahead and line these up so that they're easier to see. And so now what we have here is the discrete velocity. So for example, for our first node, we have a discrete velocity of 0, 0, and that's represented here with 0, 0. For our second one, it's going to be 0 in the x direction, 1 in the y direction, and that's right. For our next one, it should be 1, 1, and that's correct as well. And say for this for this top left one, it should be negative 1 and 1, and again, that's reflected here. So next, we're going to define our weights, and what our weights are values assigned to each one of these nodes, and they're very specific values that come from the connections that the Lattice-Boltzmann method has with the Navier-Stokes equations. Their derivations are far beyond the scope of this video. However, you can just think of them as the chance that a particle has to travel in that direction. So it has the highest chance to just stay still, and it has a much higher chance of traveling to the right than say it does to the top right. So with that in mind, we're going to go ahead and define them for each one in order, and that is going to look like this. We're going to create an array that is going to be 4 over 9, 1 over 9, 1 over 36, 1 over 9, 1 over 36, 1 over 9, 1 over 36, 1 over 9, and then 1 over 36. And this should be 9, and it is. So there are our weights, and these all sum up to 1, interestingly enough. And now we're going to go ahead and define our initial conditions. So initially, we want all of our fluid to be relatively still, but with slight inconsistencies and random perturbations. And so we're going to go ahead and define our mesoscopic velocities. So what our mesoscopic velocities are going to be are the velocities at every single cell in each one of the cell's nodes. So that means it's going to be a 3-dimensional array, 2 dimensions for the node itself, and then another dimension for each one of the cell's velocities. So that is going to look like this. And the reason I'm using numpy.1s instead of numpy.0s is simply because it's more stable. Numpy.0s collapses the simulation sometimes, and it's a very small difference that just helps a lot with the stability. And now we're going to add our random inconsistencies in the fluid to make it more realistic, and to also give it this very cool swirly effect that only comes from the slight randomness that we're going to go ahead and apply to it. And we're going to just do that with a quick rand_n function, and those are going to be our initial conditions. Now what we want is the fluid to initially be flowing to the right. So that means that we want to assign a right velocity to every single cell in the domain. And the way we're going to do that is by iterating through every cell and taking its third node, 1, 2, 3. Its third node is going to be its right velocity, and then giving it a non-zero value. And so we're going to do that by using some NumPy array notation. So at every single lattice, at every single cell, in each one of its third node, we're going to give it a value of 2.3. That's just a good value. You can play around with it. 2.3 is just what works for me. So next what we're going to do is we're going to define the cylinder. So this is going to be the obstacle that our flow is going to be flowing over. And the way I'm going to do it is a little different than how it's mentioned in the article. However, it is a lot more versatile because it will let you make your own boundaries once you are done with this tutorial. And how it's going to work is it is going to create a array that maps to every single cell in the domain, and it's going to have a value of either true or false. If the value is false, then it's just empty space, and if the value is true, then that point is going to be a obstacle. So you can set this to be whatever you want depending on what values you decide to set to true. In this case, what we're going to go ahead and do is we want to define it to be a circle. And the way we're going to do that is by first defining a very helpful distance function, which is going to help us decipher the distance in between 2 points. And this is going to take in the 2 points, x2 and y2, and it is just going to return the distance between them. And that is going to be very simple. In one line, we're just going to use the distance formula and the numpy.square-root function to return x2 minus x1 squared plus y2 minus y1 squared. And with that, then what we have to do is we have to iterate through every point in our space. And we're going to check if the current point that we're at is a certain distance away from our cylinder. So we want to check essentially whether it's within that radius so that we could set it to true and make it a boundary. And we're going to do that very simply just by doing if the distance between the point that we're at and the cylinder. So here's where we have to define where the cylinder is, and I'm just going to set it to be at nx divided by 4 and ny divided by 2. That'll put it 1/4 of the way into the x dimension and halfway in the y dimension, so it'll just be kind of around here. And we're going to check the distance in between that and the point that we're iterating through, and if it's less than the radius of the cylinder, which is going to be 13, then we are just going to set that value to true to designate it as a boundary. And here is where, after this, you're going to be able to go crazy and set this condition to be whatever you want to make whatever boundaries you want. So with that out of the way, we can enter our main loop. And the first thing we're going to do in our main loop is start iterating through time. So we're going to go ahead and print the iteration that we're at just for debugging purposes. And we are going to start with our first step, which is our streaming step. And our streaming step is, again, going to take every single nodal velocity and move it to its corresponding neighbor, which means it's going to move it to its neighbor in the direction of its discrete velocity. And we can represent that very succinctly through a loop using numpy.roll. And to avoid having to make many different for loops, we're going to use the very useful zip function. So we are going to go through every single node, and we're going to roll it in the direction of its corresponding discrete velocity. We're just going to go ahead and repeat this for y. Y is going to be our 0th axis because y comes first before x, the way we have everything set up. And that is going to be our streaming. Again, very simple for what it is. So now what we're gonna do is we are going to we're going to calculate the collisions with our cylinder. And the way we're gonna do it is by getting all of the points where the velocity is inside our cylinder. And what we're going to do at every single one of these points is we are going to invert their velocity. So we're going to set it to that velocity's opposite node. So for example, if say this is traveling in the direction of a obstacle here, if it hits it, then it would travel in the opposite direction, which means that for all of the lattice velocities that hit our cylinder, we want them to travel in their opposite directions. So the opposite direction of the 0th node is 0. The opposite direction of node 1 is going to be this node. The opposite direction of node, say 5 or node 4 is going to be node 8. The opposite direction of node 3 is going to be this node, and we're just going to do that for every single one. So the opposite direction of this node is 0. The opposite direction of this node is node 5. The opposite direction of this node is node 6. The opposite direction of this node is node 7. The opposite direction of this node is node 8. The opposite direction of this node is node 1. The opposite direction of this node is node 2. The opposite direction of this node is node 3. And the opposite direction of this node is node 4. So we are setting it to its opposite velocity when it hits the cylinder. And that covers it for that. So now what we're going to do is we're going to define the variables that we need for all of the calculations. And the first one that we're going to need that shows up everywhere is density. And the way we're going to calculate density is we're simply going to sum over all of the velocities within every single lattice. And we could do that quite efficiently using the numpy.sum function over that last axis, which is the axis with all of the velocities in them. Next, we're going to do the same thing for our momentum, except to extract only the velocity, we're going to be dividing this by our density. And again, we can do that just by doing numpy.sum f times cxs over that last axis. That's divided by rho. I'm going to go ahead and copy this. And these are our fluid variables. So with these done, now what we can do is we can apply our boundary, and we can apply our boundary by setting all of the lattice cells and all of the velocities that are within the cylinder to those opposites that we just finished calculating up here, and all of the macroscopic velocities within a boundary. Obviously, there's no fluid movement within a boundary, so all of those are going to be set to 0. So just to recap, so far we streamed all of our velocities to their neighboring lattices and to their sister nodes in the neighbor lattices. And then we set all of the velocities in every single lattice that is inside of our boundary or touching our boundary to its opposite velocity so that it bounces off. We calculated our fluid variables, and then we set all of the velocities inside of the cylinder to be 0. That way there is no fluid movement inside of a solid object, which is what we presume this cylinder to be. And now we move on to our last step, which is going to be our collision. And what collision is going to look like is like the other half of this equation. So what we're going to do is we are going to, or I should say this whole equation. So what we're going to do is we're going to first calculate our F equilibrium. And we're going to calculate our F equilibrium using this equation right here, which needs all of the variables that we just calculated. So first thing we're going to do is we're going to create an array to hold the values of F equilibrium in the same shape as the F array we had before. And again, we're going to iterate through all of our values. So we're going to iterate through all of the nodal velocities, all of the discrete velocities, and all of the weights, because that is what the equation calls for. And then we are going to calculate that the F equilibrium at every single node is equal to rho times the weights times, and then we're going to go into 1 plus 3 times Cx times Ux plus Cy times Uy plus 9 times Cx times Ux plus Cy times Uy squared divided by 2 minus 3 times Ux squared plus Uy squared divided by 2. And that is going to be our F equilibrium. And then by discretizing this equation up here, we can use that to solve for F at the next time step, t plus delta t. And we can write that in code simply by doing that F is equal to F plus negative 1 over tau times F minus F equilibrium. It's going to complain for a second there before it sorts itself out. And now we have everything calculated to then actually go ahead and plot this function and plot our solution. And what we're going to do is that to save on some computation time, we're going to create a variable called plot every, and that means that we are going to plot only every n iterations. And the way we're going to go ahead and do that is by saying that if the current iteration mod plot every is equal to 0, then we plot there. And what we're going to do first is that we're going to plot the velocity just to make sure this works, and then we'll plot the curl, which is what you see here, or the vorticity. And the way we're going to do this is just by very simply doing pyplot.imshow, which is a way of visualizing arrays within pyplot. And we're going to make it visualize the magnitude of velocity, which we can do by taking the square root of the square of the component of velocity. So we can do this by doing numpy.square root of ux squared plus uy squared. And that is going to plot the magnitude of velocity. We're going to pause for a second just to give us some little bit of time, just to give us some time to look at the graph. And then we're going to clear it to move on to the next one. So with all that in mind, if I run this, we get a solution. We get fluid passing over the cylinder. And it looks pretty cool. And if we let it run for long enough, we'll eventually see the von Karman vortex sheet appears, which is the name for when a fluid starts swirling back and forth. It might take a while here, especially since we have not adjusted our variables yet, but one thing that you notice is this rippling that happens. And this rippling happens because these boundaries right now are reflective, which means that any values that reach the walls simply get mirrored onto the other side. So instead, what we're going to do to avoid that is we're going to make the walls absorb the values. That way we don't have those waves ruining our simulation. And the way we're going to do that is by applying what is known as the Zhu-He boundary, boundary conditions. And what they're going to do, essentially, just in practice, is that they are going to set the values at the right wall, at the very end of the right wall, to the value right next to it. That way they cancel each other out. And this is going to look like this. So at that very right wall, so the last element in X, all of the values that are facing to the left, which are 6, 7, and 8, are going to equal the 6, 7, and 8 from the x value right next to it. That way they cancel each other out. And it's going to be the same thing with y, except it's going to be with a 0 value instead. Or it's same thing for the left, except it's going to be with 0 and 1 instead of -1 and -2. And with right velocities instead of left velocities. And these are our absorbing boundary conditions. If we run it, you'll see that we might get some waves. However, for the most part, they will get absorbed by the walls, and we will get a much, much smoother simulation. All of the waves that you do see here bouncing around are the ones that are bouncing from the top and bottom walls, and you can apply the same logic to set absorbing boundary conditions for the top and bottom walls. However, the simulation looks a lot better when the fluid is getting hit by those waves from the top and bottom, because it lets it reach these swirls much, much faster. So much so that if we take a look at what's going on, we'll see that we're already starting to get some asymmetries. It's hard to see, but there seems to be that there is a bit more velocity in the top than there is in the bottom, and we're starting to notice a little bit of concavity, and it's going to start to swirl very soon. And we can just speed this up by increasing our total time steps and increasing the value at which we plot every. So this should plot 2 times as fast. If you wanted to make a smooth animation of this, you would set it to 1 or 2, but for the sake of just getting through and seeing some results happen, we're going to set it to a much higher value. So I'm just going to let this run. And you'll see, again, this corresponds to the magnitude of velocity. The yellow means a very high velocity, and the dark purple means a very, very low velocity. Right behind the cylinder, you have a region of very low velocity. And that's the reason that golf balls have dents in them and aren't perfectly cylindrical, or aren't perfectly spherical, is because if they were perfectly spherical, they would have this region of low velocity behind them. That region of low velocity causes a region of low pressure, which sucks the golf ball back, reducing its speed. by having those little dimples, golf balls can develop some turbulence along their walls and can help prevent it. And you'll see right here, we're starting to get the von Karman vortex tree. Just those slight imperfections from the randomness we input into our initial conditions, we're able to create this over time. So now that we know it works, what we could go ahead and do is, instead of plotting our velocity, we can go ahead and plot our curl. And taking the curl of a vector field is simply a mathematical operation that you could look into deeper, but pretty much it just involves testing for points of essentially high swirliness. And we can calculate points of high swirliness through this equation right here. If x, y is equal to, and now we're going to do it for y. So if we take the difference of these two, we will get our curl. So dfy dx minus dfx dy, and that is going to be our curl. And what we can do is we can plot it, and we can plot it using the color map BWR, which will give red to positive values and blue to negative values. And if we run this, we should go ahead and see it. And there it is. This is plotting the regions of high and low vorticity, which is where you get these very, very cool swirls. And it's with that that this tutorial comes to an end. If you have any questions, leave them in the comments. Again, all credits go to Philip for his amazing article, and go crazy. This is a very modular piece of code, so you can edit it however you want. The Lattice-Boltzmann scheme is very, very resilient. The only thing it can't really handle are incredibly high speeds. However, other than that, you can set your boundaries to be whatever you want. You can set whatever object you so desire to be in the wake, as long as you can express it through those, as long as you can express it in grid form. And with that, thank you so much for watching.